February 17, 1982. Deep beneath the Arctic ice pack, 370 feet below the frozen surface, Commander Richard Schaefer adjusted his headset and studied the waterfall display on the BSY-1 sonar console aboard USS Dallas, a Lowe's Angels-class fast-attack submarine conducting classified surveillance operations in waters the Soviet Navy considered its exclusive domain. For the past 6 hours, his crew had been tracking a contact designated Sierra 12, a Soviet Delta III-class ballistic missile submarine returning from deterrent patrol. The target had no idea it was being followed. The Americans could hear every revolution of its seven-bladed propeller, every pump cycle, every mechanical vibration transmitted through the water. Schaefer knew the Soviet captain believed his submarine was invisible, protected by thousands of square miles of dark ocean and the Soviet Union's most advanced quieting technology. That confidence, built on years of Soviet naval propaganda and engineering reports claiming parity with the West, was about to be tested in a way the Kremlin never anticipated. The truth waiting in the deep would shatter decades of assumptions and force Soviet admirals to confront a reality they had refused to accept. American acoustic technology had turned the underwater battlefield into a hunting ground where every Soviet submarine movement was monitored, recorded, and cataloged long before those vessels ever approached striking range of the United States. In the late 1970s, the Soviet Navy had grown into the second-largest submarine force in human history, deploying more than 349 submarines of every class. Ballistic missile boats capable of launching nuclear warheads from beneath the polar ice, guided missile submarines designed to sink American aircraft carriers, and fast-attack hunters meant to destroy NATO convoys crossing the Atlantic. Soviet admirals spoke with confidence about their underwater fleet, insisting in classified briefings to the Politburo that their newest submarines incorporated sound-dampening technology rivaling anything the Americans possessed. Official Soviet technical assessments from the period claimed that Victor III-class attack submarines, introduced in 1978, had achieved noise levels comparable to early Lowe's Angels-class boats. Delta-class ballistic missile submarines, the backbone of the Soviet strategic deterrent, were believed by their designers to be sufficiently quiet to conduct patrols in the Barents Sea and Sea of Okhotsk without detection. The massive Typhoon-class boats, the largest submarines ever built, carried 20 RSM-52 ballistic missiles inside twin-pressure hulls specifically engineered to reduce acoustic signature through compartmentalization and rubberized coatings. Soviet confidence extended beyond hardware. Naval doctrine assumed that the vastness of the ocean, the complexity of underwater acoustics, and the challenges of long-range detection would provide adequate protection. Admirals assured party leadership that even if Western sensors detected a submarine, tracking it continuously over thousands of miles would prove impossible. Soviet submariners trained under the assumption that their greatest vulnerability was not being heard, but being seen during transit through shallow choke points. They believed depth and distance were their shields, that the ocean itself would hide them from American ears. Yet every assumption embedded in Soviet naval planning rested on a foundation of ignorance. The Soviet Union had no comprehensive understanding of what the United States had deployed across the ocean floor, no accurate assessment of American passive sonar capability, and no realistic evaluation of how much acoustic data the U.S. Navy had collected on Soviet submarines over 2 decades of relentless intelligence gathering. Soviet naval intelligence knew the Americans operated sophisticated surveillance networks, but the scale, sensitivity, and integration of those systems remained beyond their comprehension. This knowledge gap was not accidental. It resulted from decades of compartmentalized Soviet research, bureaucratic resistance to bad news, and a systemic failure to appreciate the American investment in underwater acoustics. While Soviet engineers focused on building more submarines faster, American scientists and naval strategists had committed to a different war, the war of listening, a silent campaign to own the acoustic spectrum and deny the Soviets the anonymity they needed for their deterrent force to function. That war was already won before most Soviet submariners ever took their boats to sea. The Americans had been listening for years, cataloging every sound, mapping every patrol route, identifying every acoustic flaw in Soviet engineering. And the Soviet Navy had no idea. The foundation of American undersea dominance was a system the Soviets barely understood and could not replicate, the sound surveillance system known by the acronym SOSUS. Developed in the early 1950s by AT&T's Bell Laboratories in collaboration with the U.S. Navy SOSUS consisted of arrays of hydrophones anchored to the ocean floor at strategic locations across the Atlantic and Pacific. These hydrophones, connected by undersea cables to shore stations, formed a passive listening network of unprecedented scale and sensitivity. The arrays were positioned along known Soviet submarine transit routes: the Greenland-Iceland United Kingdom Gap, the approaches to the Norwegian Sea, the waters near the Kamchatka Peninsula, and other choke points where Soviet boats had to pass to reach open ocean. Each array could detect low-frequency sounds across hundreds of miles, and the network's overlapping coverage meant that a Soviet submarine leaving port could be detected, classified, and tracked almost immediately. The system was entirely passive. It emitted no signals, sent no pings, left no evidence of its presence. Soviet submarines transited through coverage areas without ever knowing they were being monitored. SOSUS operators at shore stations, working in secure facilities far from public view, watch contacts appear on their displays and pass tracking data to U.S. Navy operational commands, enabling coordinated responses involving submarines, surface ships, and maritime patrol aircraft. The effectiveness of SOSUS was proven on July 6, 1962, when Naval Facility Barbados detected and reported contact number 27103, a Soviet nuclear submarine transiting west of Norway and entering the Atlantic through the Giuk Gap. That first detection validated years of research and billions of dollars in investment. From that moment forward, the Soviet Navy operated under American observation whenever its submarines went to sea. In 1968, SOSUS detected the first Victor-class and Charlie-class Soviet nuclear submarines, providing U.S. analysts with acoustic signatures that would guide anti-submarine warfare tactics for the next decade. In 1974, a Delta-class ballistic missile submarine was tracked continuously from the moment it departed its base until it returned weeks later. The Soviets never knew. They believed their submarines were operating undetected, conducting patrols in secrecy, maintaining the credibility of their nuclear deterrent. In reality, their patrol routes were mapped, their locations known, their movements predictable. American attack submarines used SOSUS data to intercept Soviet boats at sea, trailing them silently for days or weeks, gathering intelligence on propulsion systems, diving patterns, and tactical behavior. Soviet submariners occasionally detected American submarines nearby and reported these encounters as isolated incidents. They did not understand that every encounter was deliberate, that American boats had been vectored to their locations by a surveillance network the Soviet Union could not match. Soviet confidence in their submarine force was built on measurements conducted in controlled environments, in test ranges where ambient noise was minimized and acoustic conditions were favorable. Soviet engineers measured radiated noise from their submarines and concluded that newer designs had achieved acceptable quietness. But those measurements did not account for the real-world acoustic environment. Machinery noise from pumps, turbines, and reduction gears produced narrowband tonals, distinct frequencies that cut through ocean background noise and could be identified at extreme range. Propeller cavitation, the formation of vapor bubbles caused by blades turning at high speed, generated broadband noise detectable across hundreds of miles. Hull-mounted equipment, from sonar domes to ballast systems, transmitted vibrations into the water. Each submarine developed an acoustic signature as distinctive as a fingerprint, a combination of frequencies, tonals, and transient sounds that allowed American sonar operators to identify not only the class of submarine but often the specific boat. Soviet submarines were not quiet. They were, by American standards, loud, and that noise made them vulnerable in ways Soviet doctrine never anticipated. The Los Angeles-class submarine, designated SSN 688, represented the cutting edge of American undersea warfare capability when the first boat was commissioned in November 1976. With 62 submarines built between 1976 and 1996, the Los Angeles class became the backbone of the U.S. Navy's attack submarine force and the primary tool for hunting Soviet boats. Each submarine displaced 6,900 tons submerged, measured 360 feet in length, and was powered by a General Electric S6G pressurized water reactor driving a single shaft. The reactor provided propulsion for a submerged speed exceeding 30 knots, but speed was not the Los Angeles class's greatest asset. What made these submarines lethal was their silence. Engineers had designed every system to minimize radiated noise. Machinery was mounted on isolation rafts that absorbed vibrations before they could reach the hull. Propulsion systems used advanced reduction gears with precision machined components that eliminated the whine and chatter common in earlier submarines. Cooling pumps, historically one of the loudest components on any submarine, were redesigned with variable speed motors and vibration damping mounts. The hull was covered with anechoic tiles, rubber panels containing millions of microscopic voids that absorbed incoming sonar pulses and reduced the submarine's acoustic signature by scattering sound waves in multiple directions. According to declassified naval intelligence reports, early Los Angeles-class submarines generated noise signatures detectable from up to 100 kilometers under ideal conditions, but later improved variants achieved noise levels so low they could transit active sonar coverage while generating less sound than the ambient ocean environment. Yet silence alone was not enough. The Los Angeles class was also equipped with the most advanced passive sonar systems ever deployed at sea. The bow-mounted BQQ-5 sonar suite featured a massive spherical array with thousands of hydrophones arranged to provide 360 degrees of coverage. This array could detect, classify, and track multiple contacts simultaneously, analyzing the frequency spectrum of every sound in the water and comparing detected tonals against an extensive library of known acoustic signatures. Wide-aperture flank arrays mounted along the hull provided additional detection capability, particularly useful for identifying contacts at close range or in cluttered acoustic environments. Towed arrays, deployed from the stern, extended detection range even further by placing hydrophones far behind the submarine, where they could listen without interference from the submarine's own machinery. The combination of bow, flank, and towed arrays gave American submarines a detection advantage measured in tens of miles. A Los Angeles-class boat could hear a Soviet submarine long before that Soviet boat had any chance of detecting the American hunter. That advantage meant American submarines could position themselves for attack, establish optimal firing geometry, and maintain covert surveillance without ever revealing their presence. Soviet submariners had no idea how deeply they were compromised. In March 1987, the Soviet Navy deployed 5 Victor III-class submarines into the North Atlantic simultaneously, a major exercise intended to demonstrate the capability of the Soviet fleet to threaten NATO maritime operations. The deployment triggered a massive response from the United States and the United Kingdom, involving maritime patrol aircraft, surface ships, and attack submarines. American SOSUS arrays detected all 5 Soviet boats as they transited the GIUK Gap, providing initial tracking data that allowed aircraft to deploy sonobuoys and refine contact locations. 4 of the 5 submarines were tracked almost continuously throughout the exercise by coordinated efforts involving multiple NATO platforms. British and American submarines shadowed the Soviet boats, maintaining contact at ranges where the Soviet crews remained unaware of their presence. The 5th Victor III, commanded by a particularly skilled captain who employed evasive tactics and took advantage of favorable oceanographic conditions, proved more difficult to track. HMS Trafalgar, the lead ship of the Royal Navy's most advanced submarine class, was assigned to maintain contact. Trafalgar succeeded, but the mission required repeated close quarters maneuvering and demonstrated the challenge posed by improved Soviet quieting technology. Yet even that single difficult target was eventually tracked and localized. The Soviet Navy considered the exercise a success because its submarines completed their assigned patrol areas and returned to base without incident. Soviet commanders believed they had operated undetected. They had not. Every boat had been tracked, every maneuver recorded, every acoustic signature cataloged for future reference. The Soviet Union's acoustic disadvantage was compounded by espionage that revealed the scale of American surveillance capability. John Anthony Walker, a U.S. Navy warrant officer and communications specialist, began spying for the Soviet Union in 1967, passing classified information that included details about SOSUS, code systems, and operational procedures. Walker's espionage continued until his arrest in 1985, a span of 18 years during which he compromised countless naval operations. The information Walker provided allowed Soviet intelligence to understand, for the first time, that American surveillance networks were tracking their submarines across entire ocean basins. The Soviets learned that U.S. passive sonar could identify submarines by the acoustic signature of their propellers, that SOSUS hydrophones were far more sensitive than Soviet planners had assumed, and that American attack submarines were routinely trailing Soviet ballistic missile boats on patrol. The revelation was catastrophic for Soviet naval confidence. It meant that decades of submarine operations had been conducted under American observation, that patrol routes were compromised, and that the credibility of the Soviet sea-based nuclear deterrent was in question. In response, Soviet engineers undertook urgent efforts to quiet their submarines, modifying propeller designs to reduce cavitation, improving machinery mounts to minimize vibration, and developing anechoic coatings similar to those used by the Americans. Yet the damage was done, and the gap would take years to close. By the time the Soviet Union began implementing advanced quieting measures in the mid-1980s with the Sierra-class and Aquila-class submarines, the United States was already transitioning to even more capable systems. The improved Los Angeles-class boats, designated 688I and introduced in 1988, incorporated bow-mounted diving planes instead of sailplanes, allowing improved maneuverability under ice. These submarines also featured vertical launch systems for Tomahawk cruise missiles, enhancing their strike capability. Most importantly, the 688I variants were even quieter than their predecessors, achieving noise levels that made them nearly undetectable to Soviet sonar at any practical range. Seawolf-class submarines, introduced in the late 1990s, pushed acoustic stealth to extraordinary levels. At 95 decibels, a Seawolf was an order of magnitude quieter than an improved Los Angeles boat, approaching the noise level of oceanic background sound, which averages 90 decibels. The Seawolf's pump-jet propulsion system, which replaced the traditional propeller with a shrouded impeller, allowed the submarine to maintain acoustic stealth even at speeds of 20 knots, whereas most submarines were forced to crawl at 5 to 12 knots to remain quiet. The operational consequences of American acoustic superiority reshaped Cold War strategy. The U.S. Navy adopted a forward strategy that placed American attack submarines directly in Soviet home waters, operating north of the Giuk Gap in the Barents Sea and Norwegian Sea, where Soviet ballistic missile submarines conducted their deterrent patrols. This forward deployment put Soviet SSBNs at risk from the outset of any conflict, forcing the Soviet Navy to divert its best attack submarines from offensive operations in the Atlantic to defensive duties protecting their strategic assets. The strategy imposed costs on the Soviet Union, requiring increased patrol activity, more submarines, and more resources dedicated to defending rather than threatening. Coordinated anti-submarine warfare tactics combined data from SOSUS, attack submarines, surface ships, and maritime patrol aircraft into a unified tracking picture. Teams of operators at shore facilities synthesized information from multiple sensors, providing near real-time situational awareness of Soviet submarine activity across vast areas of ocean. American submarines received vectoring information that allowed them to intercept Soviet boats efficiently, minimizing the time required to establish contact and maximizing the number of targets that could be tracked simultaneously. Soviet submariners occasionally reported encountering American submarines at unexpectedly close range, encounters that Soviet intelligence attributed to chance or exceptional American seamanship. The reality was more troubling. American boats knew where Soviet submarines would be before those submarines arrived because patrol routes were predictable, departure times were known, and transit corridors were monitored continuously by SOSUS. American commanders did not stumble upon Soviet submarines. They were directed to intercept them by an intelligence network that provided precise location data updated in real time. When a Soviet submarine departed its base, American analysts knew within hours. When that submarine transited a choke point, SOSUS detected it. When it reached open ocean, an American attack boat was often already positioned along its expected route, waiting silently. The Soviet submarine would pass nearby unaware, while the American crew recorded every sound, analyzed every tactical maneuver, and reported the intelligence back to fleet headquarters. This operational pattern continued for years, an unbroken cycle of detection, tracking, and surveillance that gave the United States a comprehensive understanding of Soviet submarine operations. If you appreciate discovering the Cold War secrets that remained hidden for decades, consider subscribing to Classified Warfare for more declassified revelations that expose how technology, intelligence, and determination shifted the global balance of power beneath the waves. The psychological impact on Soviet submariners, once they began to understand the extent of American surveillance, was profound. After the Walker spy ring was exposed in 1985, Soviet naval leadership briefed submarine commanders on what had been compromised. The briefings revealed that American sensors could track Soviet submarines across thousands of miles, that acoustic signatures were on file for every Soviet boat, and that patrol areas previously considered secure were under constant observation. For Soviet crews who had believed they operated in secrecy, the revelation that every patrol had been monitored shattered confidence in their mission. Commanding officers who had reported successful deterrent patrols learned that American attack submarines had trailed them for days without detection. Submariners who prided themselves on silent running realized their boats were loud by Western standards, easily heard and identified. The morale impact was compounded by the knowledge that Soviet submarine technology lagged behind American capability not by months but by years, and that the gap was widening despite urgent efforts to close it. Soviet engineers studied captured Western components, analyzed intelligence reports, and attempted to reverse engineer American quieting techniques, but the precision manufacturing required for truly quiet submarines exceeded Soviet industrial capability. By October 1989, the challenges facing Soviet submarine operations had become undeniable. U.S. and British intelligence reported that multiple Soviet ballistic missile submarines, including a Yankee I-2 Delta IS, a Delta II, a Delta III, and a Delta IV, were all unlocated during a critical period. A Victor III operating north of Bear Island, previously tracked continuously by SOSUS, simply disappeared from coverage. These incidents represented a temporary improvement in Soviet submarine stealth, achieved through a combination of better tactics, improved quieting technology acquired through espionage and illicit technology transfer, and skilled seamanship. Yet the improvement was relative. Soviet submarines remained noisier than their American counterparts, and the challenge of tracking them reflected the difficulty of maintaining continuous coverage across vast areas of ocean rather than an inability to detect them at all. American sonar operators noted that quieter Soviet submarines required more careful monitoring, more precise sonobuoy placement, and closer coordination between platforms, but the fundamental advantage remained with the United States. Even the quietest Soviet boats of the late Cold War period could be detected and tracked under the right conditions, and the Americans had the resources, training, and persistence to create those conditions. The Soviet Union invested heavily in the Typhoon-class submarines, believing that sheer size and redundancy would ensure survivability. Each Typhoon displaced 48,000 tons submerged, measured 574 feet in length, and carried 20 RSM-52 ballistic missiles with a range of 8,300 kilometers. The twin-hull design provided redundancy and allowed the submarine to survive catastrophic damage to one pressure hull while remaining operational. Soviet planners believed the Typhoons would be too large to track effectively, that their size would allow them to carry enough missiles to ensure a devastating second strike even if most of the Soviet submarine fleet was destroyed in a first strike. Yet size brought acoustic penalties. The Typhoon's massive displacement required powerful propulsion systems that generated significant noise. The submarine's structural complexity created additional paths for vibration transmission. Despite anechoic coatings and machinery isolation, the Typhoon remained detectable at long range by American sensors. U.S. attack submarines tracked Typhoons during their patrols beneath the Arctic ice, demonstrating that even the largest, most heavily protected Soviet submarines could not escape American surveillance. The Typhoons represented a massive expenditure of resources, a technological achievement of considerable scale, but they did not change the fundamental acoustic imbalance that defined Cold War undersea warfare. American submariners developed a culture and skill set that compounded their technological advantages. The U.S. Navy maintained an all-volunteer submarine force with rigorous selection standards and extensive training. Sonar operators underwent months of schooling learning to interpret waterfall displays, identify tonals, and distinguish between biological noise, surface shipping, and submarines. Commanding officers spent years developing tactical expertise, learning how to position their boats for optimal sensor performance, how to exploit oceanographic conditions, and how to maintain contact on difficult targets without revealing their presence. Crews trained continuously, conducting exercises that simulated tracking Soviet submarines in realistic acoustic environments. This training culture meant that when American submarines encountered Soviet boats at sea, the crews were prepared to exploit every advantage. Soviet submariners, by contrast, faced different challenges. The Soviet Navy relied on conscription to man its submarine force, resulting in crews with less experience and shorter service terms. Training was more limited, in part because Soviet submarines spent less time at sea due to maintenance challenges and resource constraints. The combination of less capable hardware and less experienced crews created a compounding disadvantage that Soviet naval leadership struggled to overcome. The strategic implications extended beyond the immediate tactical contest between submarines. The credibility of the Soviet sea-based nuclear deterrent depended on the assumption that ballistic missile submarines could reach patrol areas, remain undetected, and survive long enough to launch their missiles in the event of nuclear war. If American forces could track Soviet SSBNs continuously, that credibility was undermined. U.S. attack submarines armed with Mark 48 torpedoes could sink Soviet ballistic missile boats within minutes of receiving the order, potentially eliminating a significant portion of the Soviet strategic arsenal before it could be used. This vulnerability forced Soviet planners to consider the survivability of their deterrent in ways that constrained operational flexibility. Soviet SSBNs were increasingly restricted to patrol areas close to home waters, beneath the Arctic ice or in the Sea of Okhotsk, where air and surface defenses could provide some protection against American attack submarines. These restricted patrol areas reduced the strategic value of the Soviet submarine fleet because missiles launched from those locations faced longer flight times and greater exposure to American ballistic missile defenses. The underwater surveillance advantage enjoyed by the United States translated into strategic leverage, limiting Soviet options and increasing pressure on Soviet planners to find solutions that proved elusive throughout the Cold War. The technical evolution of American passive sonar continued to outpace Soviet countermeasures. Advanced signal processing algorithms allowed American systems to extract weak signals from background noise, detecting submarines at ever greater ranges. Computerized tracking systems integrated data from multiple sensors, maintaining contact even when individual hydrophones temporarily lost the target due to environmental conditions. Towed array systems improved in sensitivity and reliability, providing American submarines with detection capability extending across hundreds of miles under favorable conditions. The BQQ-5 sonar suite underwent continuous upgrades, incorporating faster processors and improved software that enhanced target classification and reduced false alarms. By the late 1980s, American sonar technology had advanced to the point where Soviet submarines could be detected, classified, and tracked with a confidence level that transformed undersea warfare from an uncertain contest into a predictable operation. American submariners spoke of tracking Soviet boats as routine work, technically demanding but achievable with proper training and equipment. That confidence reflected not arrogance but experience, the accumulated result of thousands of hours spent trailing Soviet submarines and refining techniques that worked. The collapse of the Soviet Union in 1991 brought many Cold War intelligence programs into public view. Declassified documents revealed the scale of SOSUS operations, the effectiveness of American tracking, and the extent to which Soviet submarine movements had been monitored throughout the conflict. Former Soviet submariners, speaking openly for the first time, confirmed that they had no idea how thoroughly they were compromised during the Cold War. Interviews with retired Soviet naval officers revealed frustration with the technological gap, acknowledgement that Soviet submarines were too loud, and recognition that American acoustic superiority had been a decisive factor in the underwater competition. Russian naval analysts, reviewing the Cold War from the perspective of the post-Soviet era, concluded that the Soviet submarine force had never achieved the stealth necessary to fulfill its strategic mission, that American surveillance capabilities were far more extensive than Soviet intelligence had understood, and that the resource allocation decisions made by Soviet planners had prioritized quantity over quality in ways that proved counterproductive. The legacy of Cold War acoustic warfare continues to shape naval strategy decades later. Modern submarines remain engaged in a competition between stealth and detection, with each side developing new technologies to gain advantage. Advances in signal processing, artificial intelligence, and sensor integration promise to extend detection ranges and improve classification accuracy even further. Non-acoustic detection methods, including satellite surveillance, magnetic anomaly detection, and wake analysis, offer complementary capabilities that may reduce reliance on passive sonar alone. Yet the fundamental principle established during the Cold War remains valid. Control of the acoustic spectrum determines who controls the underwater battlefield. The United States demonstrated that superior sensor technology, combined with extensive surveillance infrastructure and well-trained personnel, could negate the stealth advantage that submarines traditionally enjoyed. Soviet submariners believed they were invisible, protected by the vastness of the ocean and the sophistication of their engineering. They were wrong. American sensors heard every move, tracked every patrol, and maintained a comprehensive picture of Soviet submarine operations throughout the Cold War. The technological gap between American and Soviet submarines during the Cold War was not inevitable. It resulted from specific decisions about research priorities, industrial investment, and operational focus. The United States chose to invest heavily in passive acoustic technology, recognizing that detection capability would determine undersea dominance. The Soviet Union prioritized building more submarines, believing that quantity and firepower would offset any acoustic disadvantage. That strategic choice shaped the competition for decades. By the time Soviet leadership recognized the scale of their acoustic compromise, the gap was too large to close quickly. Quieting submarines required precision manufacturing, advanced materials, and design expertise that took years to develop. Soviet engineers made progress, particularly in the Aquila and Sierra classes introduced in the late 1980s, but American technology continued to advance as well. The race was never static, and the Americans maintained their lead until the Soviet Union ceased to exist. Today, the Los Angeles-class submarines that hunted Soviet boats during the Cold War are being retired, replaced by Virginia-class attack submarines incorporating even more advanced acoustic technology and sensor systems. Russian submarines continue to improve, benefiting from decades of research and industrial modernization following the collapse of the Soviet Union. Chinese submarines represent an emerging challenge, with new construction and technology acquisition raising concerns about the future balance of undersea power. Yet the lessons of the Cold War remain relevant. Acoustic stealth is not absolute. Surveillance networks can track submarines across vast distances if properly deployed and maintained. Training, experience, and operational expertise matter as much as hardware. The nation that controls the underwater acoustic environment holds a decisive advantage in any conflict where submarines play a role. The United States proved that advantage could be decisive during the Cold War, and American naval planners work every day to maintain that edge against new adversaries. Join us here at Classified Warfare as we uncover the operations and technologies that kept the world on the brink, revealing the classified programs and strategic decisions that shaped the Cold War and continue to influence global security decades later.